come to the room for participation this afternoon. Good afternoon, ladies and gentlemen. Now, actually, we will have 5 speakers and 4 speakers. We have here our distinguished invite speaker, Dr. Agustus Denny Handoko. I have to read a brief CV of Dr. Handoko. Dr. Handoko graduated from NTU, Nanyang Technical University, PhD in August 2005, and then got a faculty BSc degree from same university 2001. Then he got also experience in postdoctoral in UCL London, and also in National University of Singapore, and also some thanks company to Howard Pakistan. And now Dr. Handoko is with the Electronic Material Department, Institute of Material Research and Engineering, ISCPFM, Singapore. And Dr. Handoko will talk about 2D materials for sustainable energy conversion. Without further ado, I will give you Dr. Handoko. Dr. Please, right.
Thank you, Professor Ulazwati, for the kind introduction. A little bit background about. So before I will start my presentation, I will give you a little bit of feel what is happening in Singapore. Who is ISTA? Who is Institute of Materials Research and Engineering? Before we go to the main topic. So as an overview of Singapore, we are a very, very small country. The land area is only 719 square kilometers. For comparison, Jakarta is about 662 square kilometers. So we just slightly bigger than Jakarta. 5.6 million residents. As also a comparison, Jakarta is 10 million. So Jakarta is smaller, and you have no population in Jakarta. So it's like the density is much more. But the good thing is we have very high literacy rate, 97% age 15 and above, and over 76% has tertiary qualification, meaning it's either after high school, so it's either polytechnic or university or master or doctoral degree. Mobile phone penetration rate, and it's more than 100%. So as you can imagine, like many people in Indonesia as well, one people can have maybe more than one handphone. For reason, maybe it's cheaper to call people in using different networks. This is the Singapore. This is what A-STAR's what do you call it? The overview of what we have achieved in the past year. So A-STAR stands for the Agency of Science, Technology and Research. Unlike LIPI in Indonesia, A-STAR is under the Ministry of Trade. So the main focus, the main drive of A-STAR is to advance the technology to help small and medium enterprise, small and medium company to help to realize the scientific advancement to the real manufacturing sector. So what we did, we have 340 million running. All these numbers are you don't need to remember, but like all these 4 pillars is actually saying that we focus on the industry, all the research topics, all the research activities that we do is actually focused on what the industry needs and predicting, as Professor Mulyana has already said in the keynote lecture, going forward we are going to be in the industrial 4.0. So everything needs to be digitalized. How can we help the industry towards that? A-STAR, we have 2 main branches, the biomedical and the science and engineering. So Biomedical Research Council have 13 research entities. They do research in the biomedical areas. For example, they develop vaccines, they develop new biomedical related devices like sensor, how to detect your blood glucose level without pricking needle into your skin, for example, or detecting your sweat and analyze what is the concentration to detect early stroke and so on. So Science Engineering Research Council is more like physical sciences, catalysis, microelectronic devices, and so on and so forth. ETPL is the commercialization arm. So whatever we invent, go to ETPL. ETPL try to sell it to the company. Say, okay, we have this technology. Do you want to make use in your process? And last is the A-Star Graduate Academy. Is the one that gives scholarship to local students. If they want to go abroad, they want to go to local universities, they go to the Graduate Academy. So these are the whole package of A-Star. Altogether, we have 5,000 staff. Over 4,000 of them have PhD. Okay, not have PhD, it's the research related one. So including all the PhDs and research support staff. And we are continually building international relationship and partnership. I think the picture is not drawn very well, but this is the map of the world, and this Singapore, and that's like reaching out. And this is why I'm here to meet you all. So I'm going to repeat this tune over and over again because this is a reality. The amount of CO2 is rising. Since the first detection of 1960, it's increasing, and it cannot be coincident. It cannot be cyclical because the cyclical is already reflected in the curve. And the worrying thing also is that this is the graph of the sea level detection by a satellite. So you see here from the first detection of the first available data in 1993, it's almost 100 millimeter higher now in 2018. This is the latest data I get yesterday night. So we should be doing something about it. The United Nations also recognizes this because in 2015 they launched the 17 Sustainable Development Goals, and 4 of them is actually related to the sustainability, affordable and clean energy, sustainable cities, responsible consumption and production, and action against the climate change. So what we can do in the catalysis framework. So this is a snapshot picture from a publication in my department, my group leader, Professor Sir, in Science in 2017. So this is a review article. It's a good review article to summarize what can catalysis do to create a sustainable energy landscape. This focuses on electrocatalysis, where we can convert molecules such as nitrogen, CO2, water, with the help of light and electricity to something else that we actually have already used. For example, ammonia, hydrocarbons, hydrogen, they can be, feed back to the loop and then go back to the ground again. So it's like closing the loop of the anthropogenic CO2 emission. So we are creating the energy, creating the chemicals that we're going to use in the future by recycling this, which is, you can say it's waste. So we are trying to convert waste to something else useful. First, I'm going to talk to you basic about electrocatalytic hydrogen evolution reaction. Hydrogen evolution reaction has been going around for hundreds of years. This is the first paper that reports the phenomenon of the electrocatalytic driven hydrogen evolution reaction. So this is published in, some obscure journal that has already been gone. This is actually the first scientific journal based in Paris. And the inventors are Pax van Troostwijk and Damon. So these two are the Dutch scientists. What they do is they use a Leyden jar, something like this. So this is like the very crude way to store charge. So this is like in the 1700s, these are the battery. So when you apply you connect this one to some kind of rotating, wool or something, so it creates the static electricity, and then the static electricity goes to this jar, and then in contact with the water, they saw these actually bubbles coming out from the tip, the gold tip that they in contact with water, and then they tested it, and then they named it. This is actually the composition of water to flammable air and vital air. Now we know that flammable air is actually hydrogen, and the vital air is actually oxygen. The hydrogen evolution reaction, our understanding right now, is something like this. So it's actually very simple. This is one of the mechanisms that is one of the 3 different mechanisms that is can produce hydrogen from electrolysis. So first you have proton lying around on the surface, and then after that, one of them get absorbed, and then the next one get absorbed, and then these 2 actually dimerizes and then expels as hydrogen. So this is called the Boehmer-Tafel reaction. So the Boehmer is actually the absorption of the proton to the surface, and then the Tafel is actually the coupling of 2 absorbed hydrogen and then going out as hydrogen gas. Because there's only one intermediate, so the reaction rate is actually dependent only on the absorption strength of the hydrogen on the surface of the catalyst. And then we can develop what we call the Sabatier plot, where the activity peaks at where the absorption strength of hydrogen to the surface is near 0, and actually it drops very significantly. This is a logarithmic scale when the absorption is too strong or too weak. So, but unfortunately, the catalyst that is best for HER is very, very expensive and rare. Here, palladium, platinum, rhenium, iridium, and rhodium. This is probably the most rare metal that you can find. We are proposing to use a new class of 2D materials called the MXene. MXene is actually is made from naturally layered materials for the max space. So M refers to the transition metal. X can be nitrogen or carbon, and the A is usually aluminum or germanium or silicon. So they are naturally layered. So if you just take a max space, like for example titanium 3 aluminum carbide, when you see under the electron microscope, it already looks like a lamella. So you can feel that this actually potentially can be delaminated like graphene, and then after that you can get real 2D materials. But here you need to remove the aluminum layer separating the layers. So this method is developed by the Gogotsi group in the Drexel University in Pennsylvania. So they immerse the max phase in HF and then stir it for a couple of days, maybe 2 or 3 days. And then after that, what happens is that the aluminum actually dissolve away, and then they form layered materials. And then after sonication, or if you put some kind of organic solvents like propanol, it just delaminates, and then naturally you form this. So this basically, they are just treating HF, and then you can get a 2D materials nice like this. We are proposing to use HER on MXene. So this is the first publication by also the same head of my group. This is purely theoretical paper. So what they did is they screened all the possible combination of the MXene. So the M is the early transition method in this block, and the X are the carbon and nitrogen, and then the T is actually the termination that is on top of the surface of the M. So in this case, is either mixed oxygen and oxygen-hydrogen termination. So what they find is that some of the MXene actually have the delta G H, that means the strength of the hydrogen absorption of to the surface is very, very close to 0. That means it's actually potentially very, very good for HER reaction. So we follow up. The Gogotsi group actually provided some materials to us, and then after that we treat on using different etching treatments. So it's a decreasing strength of the hydrogen fluoride etchant. the idea is that because we assume that the termination group is only oxygen or hydrogen, but this is not true, because the fluorine is actually also very sticky to the surface. Then it's gonna actually block the active reaction species. What we find is that as we change the agent from very high concentration of HF to the low concentration one, we lower the amount of fluorine on the surface. This is established by using XPS. So we just detect the amount of fluorine and then we can measure the amount of the titanium and carbon, see what's the ratio. And what we find is that the HCl performance is actually getting better and better. We do another computational and then provide different kind of treatments to the maxine of the titanium aluminum carbide, and then find that actually it follows the trend. So in the sense that the higher the fluorine amount, the higher the overpotential. Higher overpotential means it's worse OER. So the conclusion is that the lower fluorine is not very good for, if you want to produce very good catalyst for OER for HER in the maxine, you need to remove the fluorine somehow. Then we tested different kind of fluorine, different kind of maxine. In this case, is molybdenum, and then it's a molybdenum titanium mix maxine. And then we found that these are actually having much lower fluorine content on the surface compared to the titanium ones. So these are actually still following the trend. So it's like you have less fluorine, it's better HER. So that means the best samples that we have is only 200 millivolt worse, just very slightly worse than platinum. So now, what's the next step? So there's still some 20 to 100.
30 minutes.
How many minutes do we have now?
30 minutes.
30.
Yeah,
Okay. So in order to increase the HER performance even further, we did a computational studies to add in the additional atoms on top of the surface. So this is also another computational study. So we theoretically put like all the different transition metals and see actually when we put both iridium, osmium on top of the maxine surface, you can have the delta GH, which is the absorption hydrogen on the surface, is near zero. So that means this is actually giving you the even better HL performance. We are currently doing experimental validation for this. The next one is the more interesting because it's CO2 reduction to fuel. So what we do is we try to convert the waste of CO2 to molecules. This is real. It's like we can generate ethylene, ethane, methane, CO, and even ethanol or propanol using electrochemistry. It's already been known. The founding work is done by Professor Hori and Professor Azuma from Japan in the Chiba University. Copper is the most famous catalyst for CO2 reduction because it can give you is probably the only catalyst that can give you higher carbon number of hydrocarbon like for example ethanol. But the strength is because the bond strength between the copper and CO is actually optimal. But the weakness is that you have a lot of products. Like for example here, this is the real gas chromatography data. We have CH4, C2H4, hydrogen. It's very diverse, so you need to do something with the product then separate it. The problem with the copper is that now the CO binding energy actually scales with a lot of other intermediates. For example, CHO, COH, COH, and proton. So that means we also have the same Sabatier plot problem in the CO2 reduction similar to the hydrogen evolution reaction. So if we just want to use a single metal, we cannot defeat copper because it's already standing at the apex. So we need to find something else. Now we are also proposing to use maxine to do this because the surface is actually different. The surface is not transition metal, but it's oxidized transition metal. What we find here, this is a theoretical calculation. It actually opens up a new pathway through which a formic acid radical is actually more stable compared to the CO. So that means this one is actually much more, it's a different pathway compared to the single metal catalyst. And quantitatively, we tested like different kind of M2C MXene, and we found that 6 of the MXene actually can be better than copper, especially the tungsten and the titanium carbide MXene. So this is potential, the x-axis is actually the limiting potential of CO2 going to 0 is better. And then this is the difference between the CO2 and HER, because the CO2 is also done in water. If it's good for HER, it's usually not good for CO2. So in summary, MXene is a very, very promising new class of 2D materials with huge potential. The surface, why is it so? Because the surface termination is tunable. You can put fluorine, you can put chlorine, you can put any other stuff on the surface, and then you can change the properties. We have shown that it's promising for HER, and it's also possible to useful for CO2 reduction, and because it shows different pathway compared to the single metal. Together, I think we can chip in our efforts together to tackle the Earth's problem and do best what we can to prevent the global warming. And that's all for me. This is a group. I'm not the boss. This is the boss. This is our current group at the moment. This is a PhD student from Batam, Indonesia. So thank you, and with this I will try to answer all your questions.
Thank you very much. Nice talk. I think before you because you introduced to us the MXene, utility chemicals, and then we'll pray for the CO2 reduction as well.
Yes.
So I believe all my colleagues, my students here, will have a lot of questions and will be discussion, because some of them also doing electrocatalytic CO2 reduction.
Okay.
So we have plenty of time, so I invite of you to do not hesitate to have a question. Please, raise your hand.
Okay, let me give a question. Okay, thank you for the nice talk. It was very interesting to me. And I want to ask why MXene is chosen as a material for that kind of potential application, and what do the MXene have to make it really different with the noble metal? What is the big difference? I understand that based on your explanation that the noble metal have, for example, like it is not cost effective or anything else. But I'm just wondering what is the chemical, the chemical background or the chemical reason. For example, like M is transition metal, and then X is like carbon or something like this. And why we have to make something like that structure to make it as like a big potential application for that application?
Yeah. Okay. Thank you for your question. Actually, we didn't. Okay, let me start again with the theme. Yeah. So the original research of MXene is actually done by another group in Pennsylvania. They have a lot of nature science paper, and they have seen the idea is that they follow the hunch that once you reduce the dimension of a material, then you can change everything, the electronic properties, the conductivity, the absorption of light, and everything changes. Because we know from graphene, for example, graphene is chemically it's no different from carbon, from graphite, but yet why is graphene so different from graphite? So the only reason is because it's losing the what do you call it, the y-axis bonding.
Yeah.
Yeah, the sp3 hybridization is gone. So then the electron has no choice, so that it needs to travel along the plane, so that the conductivity of graphene is multiple times better than graphite. And the other interesting thing about graphene is that it's never just carbon. On the surface, you always have something, or you can put something on the surface. And once you have this something on the surface, because it's only one atom thick, it will change the binding energy of the carbon to the neighboring atoms of the neighboring carbons, and then it's going to change the properties. So with that in mind, the group in Pennsylvania and Drexel University, they are very, very interested in very thin material. In fact, they are not the only one that is interested. Professor Yi here in China also is specialized in trying to make thick materials thinner, or you build 2D materials from bottom up using ALD or something, atomic layer deposition. So in this way, they find an angle. So they saw that this is actually a repeating pattern. Why not we just take it all apart and then see whether you can make a 2D material. And then indeed, once you delaminate this structure, you see the metal bond here at the outside is actually dangling. Because it's dangling, it's trying to grab whatever that is nearby. So in this case, if you put it in water, it will be hydrolyzed almost immediately, unless there's something else, like for example fluorine or chlorine, that can bind stronger to the metal surface. Once you have this combination, even if without this one, if it is a bare one, because of the presence of dangling bond on the metals, you will change the properties simply because it's undercoordinated. Then undercoordinated surfaces is actually quite good for catalysis in general. I cannot remember your second question.
Okay. So basically, this is original idea is mimicking the graphene, isn't it?
Yeah. Something like that. And then why we thought that it's going to be good for HCI is because of the theoretical study, the density functional theory. This is a very, very powerful technique because you do not have to go to the lab and synthesize it, and then yet you can extract useful information from the material, the potential material. It may not be real. Like for example, only 5 of this M and the carbide and nitrogen is actually proven exist experimentally. The chromium one, I think, is a little bit difficult because it's not stable in air. It oxidizes straight away. But it gives you some information about if this is the ideal structure, what is the binding, what is going to be the interaction between the surface and the reactant. That is the most important. So the DFT is actually very, very powerful technique to study the materials before you even have it. So from here we already have a clue. So the interaction between the proton and the surface of this maxine is actually the binding energy of the hydrogen is actually very, very small, very, very close to zero. So this is very similar properties to platinum, and then this is just transition metal and carbon on nitrogen and oxygen hydrogen. So it's very, very cheap. Even if it's titanium is slightly expensive, but it's not as expensive as platinum. The same way as the CO2, we started the work with theoretical first, because there are more than 27 different combinations. So if we started blindly, we synthesize all the 27 and then try. And then by the end, I need probably 5 years or maybe 10 PhD students to suffer that does not have results because of this one. So that's why the computational is actually one of the first steps that we need to try to see for a new material, because it's something that is unknown, something that is new, to something reaction that is so complex. And then the second reason why the DFT is preferred, because you see hydrogen evolution reaction, there's only one intermediate, hard proton. Here you have CO2 go to the surface and then go to protonate and become COOH. And then it gets another protonation of COH, or there's another possibility that it becomes CO. And then it becomes COH or CHO. There's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Except the last one, 14 possible intermediates. And these are not all observable in real life, because sometimes the turnover frequency is so fast. The lifetime of each intermediate in real, maybe it's nanoseconds. How do you see nanoseconds intermediates in liquid? It's a challenge. So yeah. So our approach is always first try the theory first. Select which one is the promising, then we go on experiment on that few select materials. Then we prove the theory, and then that's the positive feedback loop.
Thank you.
Okay. Yeah. Interesting discussion. We should bring to other partner in this discussion.
Yes.
Okay. Then I invite all our students. Don't hesitate. You may also ask in Bahasa Indonesia. Actually, Dr. Handoko also fluently in speaking Indonesia. So don't be hesitate.
I speak in English because this is supposed to
Yeah.
be international, so
Right.
it's good training for the students as well.
Yeah. Okay. Yeah. Dr. Handoko.
So how about the competition with the hydrogen evolution?
Oh yeah. Okay. That is a very good question, because this the competition with the hydrogen evolution reaction is actually very, very fierce. As you see here, actually we have this matrix called UlCO2 minus UlH2. So the UlH2 we can also calculate because we know the structure, and then we know the intermediates of hydrogen evolution reaction is hydrogen. So that means the delta G, the absorption strength of the hydrogen, can be directly translated to the limiting potential. So for example, if you're limiting your bond strength of the hydrogen to your surface is 0.1 eV, then your theoretical, the lowest possible limiting potential for hydrogen evolution is 0.1 volt. So that means it's actually very, very good for HER. Then we compare this with the limiting potential of the CO2 reduction. How do we get the CO2 reduction limiting potential? It's from this graph. So the limiting potential is actually the highest difference between the intermediates. For instance, in this example of Ti2C, O2 is actually the dominating species on the surface. You see here, from CO2 to COH is downhill, so there is no restriction. It will go, this is exotomic reaction, it's instantaneous. And then it goes to HCOH, this is also negative, so this is instantaneous. But it goes to CHO, this is become endothermic, so the difference is about negative 0.14. And then after it goes up again, so the biggest difference that we find is actually the desorption state. So this is where we find the potential UL, the limiting potential for CO2 reduction. So this is from the theoretical point of view. And then we compare the UL for CO2 and then the limiting potential for hydrogen, and we find that molybdenum is the worst, because we know from the previous study molybdenum carbide is actually the best for HER. The limiting potential is very, very close to the tip of the volcanic curve. and then after that, those here is actually the worst for each year. The tungsten, titanium, chromium, titanium, niobium, vanadium is actually horrible for each year when we did the first theoretical study for each year. And then when we subtract the hydrogen limiting potential with the CO2 limiting potential, then we find that on this corner is actually the most promising, because then tungsten is particularly interesting because the difference is positive. So that means it refers to the CO2 compared to the hydrogen solution fraction.
Interesting. Any other question? So I will take my chain of question. So can I have a slide with the review in the side?
Yeah. Review.
Yeah.
Okay.
Okay, yes. Okay, you also mentioned about the nitrogen conversion by electrocatalysis,
Yeah.
something.
Yeah.
It's with in room temperature to convert nitrogen to ammonia something.
Yes.
And how do you do this?
Currently, I don't know, but there have already been some reports.
Mm-hmm.
The periodic efficiency is very, very low, 1%
Yeah.
or less,
Yeah.
but it is doable. I think they did they just bubble in ammonia in the some kind of organic solvent. I can't remember. And then after that, this is our really like a future step. So I haven't really looked into it, but I have seen some papers. It's possible. Yeah.
Now we are trying to do this. In fact, my student now, PhD in second year, doing into conversion to ammonia by photocatalytic modified setting.
Oh, modified setting. Yeah,
So I'm interested. So I'm
Yeah.
looking for your future result.
yeah. Yeah. I think in the thermal catalysis, it's already proven. I mean, it's already industrial. Yeah.
Haber-Boschman.
But yeah, yes, Haber-Boschman. And in electrocatalysis and photocatalysis, I think photocatalysis is even more challenging because you get a lot of electron and proton loss everywhere.
What we have only 0.002 heat per centimeter.
Okay,
Just
it's a start.
Starting.
It's a start. Yeah, but it is possible. It is also very, very lucrative. There is also, if you can really develop a process that can replace Haber-Bosch process, it's you probably can build another country.
Okay. Can we still have time? So if anybody have a question, go ahead. Student? Oh, where's my student? Nobody coming here from my group. Okay. I encourage one question from student. This. Can I stay? No?
It is also possible to ask in Bahasa Indonesia. It's fine.
Yeah. Come on. Tidak apa ya? Ini dari grupnya nih semua yang lagi bawa penelitian kan? Masih nggak ada di sini ya berarti? Oh.
Ini grupnya Pak Asep ini.
Ayo.
Mana? Ya, grupnya Bu Rika mana? Ayo.
Oke.
Oke.
Saya tidak mau masak. Okay, some of students are working on CO2 reduction electrocatalysis by within Pembicara ini, and in my group also using with copper oxide something. Yeah.
Okay.
And then so now my PhD student working on photocatalytic conversion of nitrogen to ammonia.
Okay.
Yes. Yeah. One or two students in master degree also do that, but the result is still low, but we try to improve the process.
I think the most challenging part is to get the setup running in terms of the detection. I think to get the really quantitative, valid quantitative data of the product.
That's why I also do Kyoto next month to get the quantitative data of that conversion. Okay. If no question from audience, then okay, time is almost.
Nasional matematika
Okay.
yang
Then let's join me to give big applause to Dr. Handoko. The organizing committee will prepare some other honor presentation in it for writing. Then I will give some token to the Handoko from organizing committee. Again,